Next we will discuss more about feedback systems. Okay, so what are the effects of feedback? We saw that a feedback system or a closed loop system, it can be represented in general like this. Okay, so here you have the feedback. This is the input, let us say R of S, and this will be the output, let us say C of S. Okay, so this will be the forward path transfer function, this will be the feedback path transfer function. Okay, now the feedback, it can be either positive or negative. Okay, so whatever it is, we can see that the output that is taken from this point, it is being fed back as a feedback signal after going through the feedback path transfer function. Okay, so this, if you take the signal to be E of S here, the error signal, okay, then E of S is dependent on the output, that is C of S, right? And in turn, E of S will affect the output. Okay, so C of S is also dependent on E of S, right? So we can see that C of S will affect E of S, and again E of S will in turn affect the C of S. So we can see that there is a closed sequence of cause and effect relationship. Okay, so this is what will be present in a feedback system. In a feedback system, there will be a closed sequence of cause and effect relationship. Okay, here the feedback, if it is with a positive sign, okay, then it is called as a positive feedback system. Okay, and if it is, this is for positive sign. If it is negative sign, okay, then it is called as a negative feedback system. Okay, so we will mostly encounter negative feedback systems, okay, because positive feedback systems, they are for some specialized applications like oscillators. Okay, what is the transfer function of positive feedback systems? It will be G by 1 minus GH, and for negative feedback it is G by 1 plus GH. Okay, so we have discussed this previously also. Next we will see effects of feedback. Okay, that is, if for a system you are including feedback, then what will be the effect on the some parameters. Okay, so the first parameter that we are going to say is gain. Okay, now if you consider a open loop system, open loop system will simply have one forward path. Okay, so this is G, this is the input and output. Okay, and for a closed loop system, you will have a forward path and a feedback path, right? So this is G and H, input will be here, output will be here. So now we can see that the transfer function for a closed loop system, for an open loop system, this will simply be equal to G, right? But for a closed loop system, the transfer function will be G by 1 plus GH for negative feedback systems and G by 1 minus GH for positive feedback systems. Now here you can see that 1 plus GH, it will be greater than unity, right, because something is being added to 1. So 1 plus GH will be greater than unity. Okay, and 1 minus GH will be lesser than unity, right? So G by 1 plus GH, this will be less than G. Okay, and this is the closed loop transfer function for a negative feedback system, and this is for open loop systems, right? So compared to a open loop system, the gain of a negative feedback system will reduce by a factor of 1 plus GH. Okay, and if you take the positive feedback systems, then G by 1 minus GH will be greater than G. Why? Because 1 minus GH is less than unity. Okay, when you are dividing by something less than unity, it will become greater. Okay, so this is open loop and this is for closed loop positive feedback system. So for a positive feedback system, the gain is increasing by a factor of 1 minus GH. Okay, so one important point that you have to note here is, in general this is correct, okay, but GH, these GH values, if they are of negative value, okay, then this result will be inverse. Okay, but if they are positive value, then this will be the case. The next parameter is stability. So for an open loop system, stability is not a big problem, okay, but for closed loop systems there might be stability issues, okay, and the negative feedback will have stabilizing effects. Okay, it has the capacity to stabilize a system, but positive feedback, it can destabilize the system. Okay, so this is one advantage of negative feedback systems. The next one that we have is sensitivity to parameter variations. Okay, so we know that a control system, it is made up of a lot of components, and these physical components, they will have some parameters that are associated with it, right? For example, if you have a resistor, then you have a resistance associated with it. Okay, and similarly if you have a spring, let us say, then it will have a spring constant associated with it. Okay, now these parameters, they may vary over time because of aging, okay, because of wearing out. Okay, so what will happen when there are such variations, and how is the sensitivity, that means how much the variations in these parameters is affecting the overall system. Okay, that is a sensitivity. So we will now see, we will now compare what is the sensitivity to the parameter variations for open loop system and closed loop system. Okay, so how will the feedback affect this sensitivity? So again, if we draw a open loop system, this will be G, and a closed loop system will look like this. Right, so this is G and this is H. So here we will consider negative feedback systems only, because like we said, we often use negative feedback systems, while positive feedback systems, they are used for some specialized applications. Okay, so we will discuss the sensitivity of negative feedback systems. So this will be input, let us say R of S, okay, and output is C of S, and feedback will be negative. Now let us say the transfer function of this closed loop system, it is M. Okay, now the sensitivity of M with respect to, first we will consider the forward path transfer function. Okay, so for any variations in G, how will M vary? For this we will define one expression as mg. Okay, so this is defined as percentage change in M for a percentage change in G. Okay, so percentage change in M means that it is given by dou M by M. Okay, change in M divided by M, that is the percentage change in M. Similarly, percentage change in G will be change in G divided by G. Okay, so this will be G by M, dou by dou G of M. That means you are partially G by M into partial differentiation of M with respect to G. So we got sensitivity of M with respect to G is given by G by M into dou M by dou G, right? So this will be equal to G by, what is the transfer function of a negative feedback system, it is G by 1 plus GH into dou by dou G into G by 1 plus GH. Okay. So, this expression you are differentiating, you are partially differentiating with respect to G. So, this will be equal to 1 plus GH into 1 plus GH, the denominator, into dou G by dou G, okay, differentiation of numerator, minus G into dou by dou G of 1 plus GH divided by 1 plus GH whole square. Okay. So, this you will get as 1 plus GH into 1 plus GH, dou G by dou G will be 1, okay, minus G into dou G by 1 plus GH will be 0 plus H. Okay. So, this you will get as 1 by 1 plus GH. Okay. This is for a closed loop system, negative feedback closed loop system. What about the sensitivity of transfer function with respect to G when it is a open loop system? So, for an open loop system, the transfer function is simply equal to G, right? So, this when you write G by M into dou M by dou G, okay, then M will simply be G into dou G by dou G. This will be equal to 1. Okay. So, if you compare the sensitivity of closed loop system, a negative feedback closed loop system, with a open loop system, okay, you see that the sensitivity is lesser for a negative feedback system by a factor of 1 plus GH. So, which one is more desirable? We want the sensitivity to be lesser, okay, even if there are variations in parameters, we don't want those variations to reflect on the overall transfer function. Okay. So, the sensitivity should be less. That means the negative feedback system is more preferable because its sensitivity to variations in parameters is lesser. Okay. So, this is the advantage of a negative feedback system. Similarly, you can find out the sensitivity of the transfer function with respect to the feedback path transfer function, which is H. Okay. So, this will be equal to percentage change in M divided by percentage change in H. Okay. So, this you will get as H by M dou M by dou H. So, H by M into partial differentiation of M with respect to H. So, here we can write G by 1 plus GH into dou by dou H of G by 1 plus GH. Okay. So, this you will get as H into 1 plus GH by G into minus G by 1 plus GH whole square into G. Okay. So, this you will get as minus GH by 1 plus GH. Okay. So, this negative sign here, you don't have to worry about this sign when it comes to sensitivity, because it's only an indication of whether some variation is bringing about a change positively, that is whether it is increasing or decreasing. Okay. What we are concerned only with the magnitude, how much is the change. One thing that you can notice here, the sensitivity of transfer function with respect to H, it is greater than the sensitivity of transfer function with respect to G. Okay. So, we saw that this was GH by 1 plus GH. Okay. This is only the magnitude. Okay. This is greater than 1 by 1 plus GH. This was the sensitivity that we got for forward path transfer function. Okay. So, this is one important point. It means that the system is more sensitive to variations in the feedback path. Okay. That is why we often see to it that whatever elements, whatever components that we are using in the feedback path transfer function, they do not have much variations, okay, so that if there are no variations, then there will not be any effect, okay, so that we take care. So this sensitivity with respect to feedback path transfer function, it will only exist for a closed loop system, right, because for an open loop system we just have forward path transfer function, which we do not have any feedback path. So we need not have to compare with the open loop system. The next parameter that we are going to discuss is the effect on disturbances, okay. So let us say we will take a open loop system which is having a disturbance like this, okay. This is G1, this is G2. We have some disturbance input, okay. Disturbance is nothing but an unwanted signal, okay. So we can take it as some signal that is being input to the system, okay, and our input is R of S, output we will get as C of S, okay. And similarly, if we have a feedback, then the diagram will be like this. Here you have a disturbance input. We will take the feedback like this. Okay. So disturbance input is being added. Okay, this is the output. Now how will we find out the effect of the disturbance? The effect of disturbance we can find by the transfer function C of S by D of S when the input is equal to 0. Okay. So this gives what is the effect of the disturbance in the input in the system. Okay. So for open loop system, this will be equal to simply G2. Okay. If R of S is equal to 0, then this is the simple block diagram. Okay. So this will be the transfer function. So what will happen in the case of closed loop system? Here C of S by D of S when R of S equal to 0. Okay. How will the block diagram become? It will be, here we can have D of S, this is G2, okay, and here you will have H, this will be added negatively, okay, or you can simply take it as minus H, okay, because R of S is 0. So for this summing point only there is only input from one side, okay. So we can remove the summing point altogether and we can include the negative sign in the block itself. So this again it will go to G1, okay, and this is going to the summing point, okay. So this is being added positively, okay. Here also instead of this positive sign you can put negative here and you can put positive at this place, at this block, okay. Now we have a negative feedback system. So what will be the transfer function here? This will be equal to the forward path transfer function, which is G2 in this case, divided by 1 plus, because there is a negative feedback, G2 into forward path transfer function into the feedback path transfer function in this case is G1 into H, because they are in cascade. So G1 into H. This will be the transfer function due to the disturbance input, okay. So if you compare this and this, you can easily see that this transfer function is reduced by a factor of 1 plus G2 G1 into H, okay. So the effect of disturbance will be lesser for a closed loop system, a closed loop system with negative feedback, okay. So this is the advantage. Whenever there is a disturbance in this place, remember that this disturbance we have taken at one particular location. If the disturbance occurs elsewhere, then case might be different, Okay, but for this case that we have discussed, that is a disturbance in the forward path forward path, then the open loop system will have more effect because of the disturbance, and for a closed loop system the effect of disturbance will be lesser. So we have discussed gain, stability, sensitivity to parameter variations, and finally effect due to disturbance. Right. So now we will see what are the advantages and disadvantages of a feedback system when compared to a open loop system. Okay. So first and foremost, the primary objective of feedback also. What is the primary objective? We tend to correct any deviations in the output. Okay. So we can monitor the output and we can correct any deviations in the output in case of a closed loop system. Okay. So these are the advantages. We will first discuss the advantages. Okay. This was the very reason, this is the primary reason why we use feedback. Okay. But once we start using feedback, then we will have some more advantages. Okay. So we saw that the effect of disturbance is reduced. This is one advantage. And sensitivity is another advantage. We saw that the system will become less sensitive to any variations in the parameter. Okay. And one more advantage we have, this will become more clear when you do time domain analysis. Okay. The speed of the response is increased. Okay. So this, what is meant by speed of response, all this we will understand in the time domain analysis. Okay. So these are the advantages of a feedback system. It also has some disadvantages. Okay. The first and foremost disadvantage is that it is more costly, right? Why? Because we are including more elements. For an open loop system, we simply have one forward path. But for a closed loop system, we have a forward path and also a feedback path. Okay. And there is an error detector. So obviously it will become more costly and also complex. More number of elements, more will be the complexity. Okay. The more things that you have to analyze. And second thing we have discussed in stability, there will be some stability issues. Okay. For an open loop system, there will not be stability concerns, but for closed loop systems, there might be some stability issues. That is why we have a whole chapter discussing about stability. Okay.